guys, welcome back to my YouTube channel, Teacher Dex Channel TV. Today is January 29. It's already 7 or 6:50 in the morning. I would like to welcome you again in my online classroom, or it is our online tutorial. So I'll be discussing with you about magnetic flux. Before, I already presented with you magnetic force, magnetic field, and we have the centripetal force, the relationship of the three scientific terms. This time, I'll be discussing with you what is magnetic flux. So, ayan nga. So, when we say magnetic flux, it all depends on the magnetic field in the region of space. Okay, such as the region inside a loop of wire. Okay, as we all know in the magnetism, lines drawn from the north to south, that is the direction of the magnetic field. Okay, when a core or loop of wire is placed in a magnetic field, some of the field line pass through the loop. So it all depends on the loop, or it all depends on the region of space in the magnetic field. Okay? Now, the magnetic flux through the loop equals of magnetic field that pass through the coil and depends on the area. Okay? And the magnetic field and the orientation of the loop in the field are always equal to the magnetic field. Now, let us try to see. When the plane of the loop is parallel to the field, no lines through the loop, and the magnetic flux through the loop is zero. If the loop is rotated so that its plane becomes oriented nearly perpendicular to the field, more lines pass through the loop and the magnetic flux increases. So always, as we all know, if it is in parallel, the angle is zero. We will be using the trigonometric function, which is cosine. When we say cosine 0, it is equal to 1. But if you're going to use a cosine 1, and that is equal to 0. Okay? So let us try to see again. Based on this, we have our magnetic flux. Okay? Magnetic flux equation. So our magnetic flux equation is denoted as this one, which is equal to AB cosine theta. AB is area, B is magnetic field, and the angle. Okay? How are we going to solve our area now? Area is pi r squared, which is always in meters squared. Okay, so this is our magnetic flux. As I've told you, if the line is perpendicular to the area inside the loop, magnetic maximum flux perpendicular line, if it is perpendicular, is 90. Okay, cosine 90 is equal to 0. Cosine 0 is equal to 1. But always remember, this is a parallel line. So if it is parallel line, it is always equal to 0. There is no increasing of the magnetic flux. So it's always 1. It's always 0. Cosine 0 is always 1. But if you're going to make it perpendicular, cosine 90 is equal to 0. Always remember that magnetic flux plays an important role in electromagnetic induction. So we will try to see the relationship of the magnetic flux in electromagnetic induction. As you notice that as the bar magnet moves closer to the loop, the flux through the loop increases. But when the magnet is withdrawn, the flux decreases. Kapag malapit po yung bar magnet sa loop, of course, the loop increases. Kapag nilayo po natin, nagde-decrease po yun. Okay? So electromagnetic force and the current is induced in the coil. Okay? If the magnet is not moving, the flux does not change and the current is zero. So that's what we call cosine zero is always equal to 1. Let us try to see how this induced electromagnetic induction is derived from the equation. So E is denoted as electromagnetic force, which is equal to negative n, the number of turns of the loop, multiplied by, we have to multiply by the change in the magnetic flux. Okay? Magnetic flux po yan over our change of time. Okay? Therefore, we can say that induced electromagnetic force is equal to negative NA cosine theta multiplied by the change in the magnetic field, which is B minus original magnetic field. So final field minus the original field over the change of time, which is final time minus the original time. Okay, so this is our formula in solving our induced electromagnetic force. But always remember, induced electromagnetic force, the unit is in volt. Okay, change of magnetic flux. Okay, change of magnetic flux is equal to Tesla meter squared. Tesla meter squared. And of course, the change of time is in seconds. So these are the units that we have to get acquainted with. So here's the problem that we are going to solve to apply the magnetic flux and induce electromagnetic force. So I would like to read with you. A circular loop of wire with 50 turns and a radius of 2.0 centimeter is moved from outside to between the poles of a horseshoe magnet in 0.10 seconds. The field between the poles is 0.18 Tesla. Find the average induced electromagnetic force as the loop moves into the magnetic field. So that is the problem for the application of our induced electromagnetic force. So ang hahanapin po natin is the average induced electromagnetic force. So what are we going to do first? We have to identify again all the given. So given in the problem are, first we have our n, which is equal to 50. Okay, we have our radius, which is 2.0 centimeters. Then we have our time, which is 0.10 seconds. We have our magnetic field, which is 0.18 Tesla. Find the induced electromagnetic force. Okay? So, meron tayo, wala always, remember that our angle is always in parallel. So, it is 0. Okay? First, wala tayong area. Area ang hahanapin natin. So, how are we going to solve the area? We're going to use the formula, which is area is equal to pi r squared. Okay? So, pi r squared, so we have 3.1416. Okay? I-convert muna natin ito. So, divide both side. So, we have this. We have our area or our radius, which is divide natin into 1,000. So this becomes 0.004, okay, meters. So let us try to see if it's correct. Let us try to use our calculator. So our calculator will reveal, okay, so we have here meter square po ito. So 20 divided by 1,000 times 2. 20 divided by 1,000 square meter. So we have here 0.00, or this is what we call 4.0 times 10 raised to negative 4. Okay? So times, gawin natin pong normal ito. 0.0004 times 3.1416. Okay, so we have here our area is 1.26 times 10 raised to negative 3, or we can say it is 1.3. Okay, so based on that, we are going to use this as our area. So induced electromagnetic force is equal to, our formula is negative NA multiplied by cosine theta multiplied by the change of magnetic field over the change of time. So we have here 50, okay, multiplied by 1.26 times 10 raised to negative 3 multiplied by cosine 0 multiplied by 0.18 Tesla over our change of time is 0.10 seconds. So if we're going to solve this, our answer is equal to, we have negative 0.12 volt. So that is our solution for our problem. Okay, so this is our solution. So guys, thank you very much. That is our topic for today. It's all about magnetic flux. If you like this video, do not forget to like, subscribe my YouTube channel, Teacher Dex Channel TV. Thank you very much. God bless everyone.